Hi everyone, in this lesson we are going to look at the distinction between rate equation or an overall equation and also how we can use that in our mechanism. So for the chapter of kinetics, right, one of the important things behind studying this chapter of kinetics is to study the mechanism of a reaction because we want to know how a reaction works and how we can use different how we can change different concentration, right, based on the mechanism to affect the rate of reaction. Okay, because if certain reagents is in the fast step, changing its concentration is not going to lead to a change in the rate of reaction. So that is why it is important for us to study the mechanism. So I think this mechanism that's written over here should be quite familiar to you. This is our SM1 mechanism. If you haven't learned the chapter of halogen derivatives yet, then this will be something new to you. So like every reaction with more than one step, all right, we always have a slow step, and every other steps connected to it, it could have five other steps. They are all considered fast. So the slowest step is the one that usually gives us that actually gives us the rate that actually determines the rate. So the slow step is what we call the rate determining step, right? So this is called the rate determining step. So every other fast step is not important, or what is important is the slow step. So we typically write our rate as rate is equal to k times whatever we have in the reactant side of the slow step, which is this reagent. Okay, and it is only the first order with respect to this, and that is all we have for the rate equation. And then how do we get the overall equation? We actually add all of these things together, and we realize that if I were to add both sides together, this carbocation here is repeated, right? In fact, this is the intermediate which is produced and consumed in the next step, so I will have to remove it away, and I'm going to add everything on the left hand side together and add everything on the right hand side together, and this will give me the overall equation. So our job here is to remove all the intermediates when we want to form the overall equation, right? So to form the overall equation, we remove the intermediates and just add everything else together. But for the rate equation, what we want to do is we look at the reactant of the slow step and then we put it here. All right. However, if we were to consider this equation here, okay, if we want to write the overall equation, we'll add all of these things together. Since C is the intermediate because it was formed and removed, then our overall equation becomes A plus B plus D over here, and it gives you E. However, in this case, the slow step is our second step, right? It is no longer our first step, so we need to take an additional step over here. So as usual, we have rate is equal to K times C times D. So I'm just using these values here. And so what happens is I'm going to skip away all the mathematical steps in the middle and just come up with a new proxy for this answer. Right, so what we are going to do here is that because C is an intermediate, there's no way that we can include C into our rate equation because it does not exist here. So because our rate equation is rate is equal to K times A, right, to the power of X, B to the power of Y, and D to the power of Z. So there's no C in this equation, so we want to make it such that it looks like A, B, and D. Okay, and we know that C is from the fast step and it has to be created from A and B. So with that, I can actually replace A and B, replace C with A and B. But of course, there is a constant at the side, so I'm going to chuck it into this K, and so I will get a K prime A, B, and D, where the A and B actually came from C because C was consumed and C was formed from A plus B. Okay, so I hope this is able to help you to explain how explain the difference between rate equation and overall equation, and also allow you to write out the rate equation using the mechanism, regardless of whether you're given the slow step as the first, second, third, or any other steps in the reaction.